Yeah, hi, am I audible? Hi, am I audible? Can you please anyone respond? Hello, can anyone respond if I am audible or not?
Hi.
Yeah, so let's wait for 2 3 more minutes. Let's see how many more people join. We'll start at 6 to 6:03 around.
So can I ask you something?
Yeah, you can ask.
Why we have two problem sessions, like one in Friday and one in Monday,
Yeah, actually there are three
and
problem
both.
sessions. Yeah, so the thing is there are separate TAs for it. So I mean there are many who have enrolled for the course. So everybody don't have the time to be present at the same day. So it is left upon the user's preferability to where to join. Okay, so you can join on any one of them.
Okay, but we don't have any problem sessions in computer architecture or number theory.
Architecture, there is no problem for solving session.
No, I never got any mail from computer organization or architecture.
I mean that is very bad because last in 22 I was the TA for computer organization and I was uh, so I used to conduct it. So this session I guess nobody has been assigned that one.
No, I don't got any mail from operating. Sorry, computer architecture.
Yeah, so I guess they are not conducting any session for that. Maybe that may be a case. So who is the professor there?
That is actually cool, but I have something to ask, but I don't have any solution to touch with them.
Okay, you can if you want any such solution, you can mail me. Okay, so I can help you. That's not an issue. Okay, so let's start now. There are let's not wait much more. Okay, so hello everyone. My name is Srijay Mukherjee, and I am a research scholar in the Department of Computer Science and Engineering, IIT Kharagpur. We will be solving some problems related to this week's NPTEL course on operating system fundamentals, as well as we'll be clearing some of the doubts regarding this week. So this session is being recorded. Also, feel free to ask any question whenever you have any. So let's start. So at the beginning, we will be doing some recap of this week's class in a very short time. So let's start. So let's come to the slides. Okay. Yeah. So so if you recall last week, we were looking at the procedure on how to create a process. So as you know, so we use the fork function to create a process from a process that is being running. So when we use a fork, one process is created. So that is called the child process, and the parent runs on its own and the child runs on its own. Some places you can use the child and the some places the um, parent process may ask that I will wait until my child finishes his or her job. So that is one situation. But generally, this is the case. So let me draw some diagram to explain what I wanted to say. So you have a process P, In that you have written a code id is equals to fork. Okay, so this part of the code, so this is your process parent. Now when you run the parent process and this part of the code is encountered, so it creates a child. So what happens here? What does fork return? Fork fork return the process ID of child. Okay. So what happens in this if statement? So when this is successfully executed, the parent process will run this part of the code. Will run this part of the if statement. Or suppose there is also an else block. What will the child do? The child will run this else part of the statement and the rest of the code. Now suppose the parent wants to know when wants to wait until the child finishes its task. So it is suppose adding some like appending some lines into a file. So the parent may ask like I want to wait until the child finishes his or her task. So what he can what can the process can do? So it will the programmer can write a wait statement and put the process ID here. What does the wait statement do? The wait statement basically waits until this process is terminated. So as long as the child is running, the parent process will wait and observe how long it is active. Once the child process is terminated, it will come out of this wait state and it will complete its part of the code. Okay, so this is the function of the wait statement or wait function. Okay, so any doubt regarding fork and wait? So, so how can the child says that it has like how does the child kill itself, or how does the child wants to suppose the child wants to get out of its running state? What can it do? So one procedure is exit. So suppose this in this else part there is a exit command. So when the compiler or the operating system encounters this exit, it signals the wait the process has terminated. This is also another way of forcefully exiting from the child. Clear this parent child wait and exit statement and how it works? You can ask any question if you have. Okay, so we will be looking into some codes of how this fork works in a few minutes. So let's come back to the slides. So a process termination. The process terminates when it executes its final statement and it asks the operating system to use the exit system call. Process can parent itself can also terminate the execution of child process using abort. Abort is another command where which the parents uses to terminate the child. The way it is used the way it is used the parent process wait use the wait for termination of the child process. This is another system call. Okay, so now let's look at how this uh, programs works. Is this visible?
Yes, sir.
Yeah. So let's look at this thing. So in the shell, you type this in your Linux system, grep trick trek.txt, and another, suppose you have this grep try next.txt. So grep is a program, okay, and what it does, it searches inside this text file whether this click is present or not, and similarly here Troy is present or not. It is like a like pattern matching kind of program, grep in C. So what it does, so now you run this code, and you go to your system and type ps minus ef. It gives you all the corresponding time related to it. So you will get the uid, you will get the process id, you will get the parent id of who started this, and as well as the command that is being running. So what is uid? Uid is the user id. So Neil is running this code, so its user id is this Rick and Neil here, and Rick is running this code, so its user id is Rick. And this is the process identifiers. These are all the uh, uh, available information you will get while running this code. Now let's come to another thing. So what does ps minus ef gives? It gives you all the running processes in your Linux system. Now let's turn to how process works. So you know this system command. So what does the system command done? So you want to run something on your on your terminal. So you want to run something on your terminal. So you write this code. So you write uh, this code, and so running ps with x. So what does this does? This system ps is basically telling the operating system that give me the list of program that is running currently. Okay, so what happens here? This creates a process. So this uh, system colon psax is, it creates a process. So this process runs this ps minus aex. Okay, so consider it like this. Consider it like this. 1 minute. Uh, Consider it like this. So you have your system, you have written ps minus s, and this is your C code, and you run this C code. So when you are running this C code, so suppose you have saved it as axt.c. So you are running this C code, it becomes a process. Let's say it becomes axt.p. So this is a process that is running. So what does this process does? It's come to this portion and it creates another process, ps minus q. which leads all the processes. So what happens in this case, your program waits until it completes this statement, and then it joins back, and then it runs for the execution. So this is how your system call works, your system command works. Now there is a particular difference between how this works and how your fork works. So how does your fork work? Let me come to how does your fork work. So this is how your fork work. You have your initial process, you fork it and it creates a new process, and whereas the child remains as it is. So while in a fork our relationship is like this, a new process is created. So this is parent and there is child. In a system there is nothing as parent or child. So one process, it's create another process, it completes it, and then it continues. There is nothing this kind of scenario. Now let's look at some code which runs this fork. Okay. Here is a simple code which creates a process and runs it. So let's look at this main part. So here is your process ID, you have taken a message and something. So here you are doing your fork, and then there is your switch statement. So this PID is basically the process ID of your child. So this switch command, so if it is -1, PID is -1, that means fork failed. If it is 0, that means it is the child, and the message will be this is a child. And if it is some other thing, it is the parent. This is how the fork, you can write a fork in your uh, program. This is how fork works in C. Uh, okay, and here is how your wait works. So here is your system val. This is your PID. So this code will work only if, so only when it is a parent process, and it waits until and unless the child is finished, it's terminated or not. Once it is terminated, you can just terminate. You can just find it here, the system val. So this is your wait. This is how you write a program for for creating a process as well as for wait. So here is your fork. So after fork, if it is a child, it will not enter here. But if it is if it is like your parent, it will come here. It will wait until and unless your child is terminated. This is how it works. So one more thing, a parent can produce more than one child. Okay, it cannot have more than one, that only one child. So what I mean to say is this. So here is your parent program. It can do one fork, it can do another fork, it can do another fork. So what happens in this case is there are multiple childs that are being produced. So after doing these 3 forks, how many childs will be created? If we apply 3 forks at a time, how many childs will be created? So this is your parent, one fork. So here comes the parent, and here comes the child one. Now here comes the second fork. Here is your parent, here is your child 2. Now this child will also prepare this, so it will become another parent, C4, right? And next, when this fork comes, P, C5, C6, C2, C6, C1, C3, C1, C7, C4, 5. Okay, let me do it again. So what I am saying is, you have a
Sir, can you
program.
explain
Yeah, I am
me?
explaining. I am explaining again. So you are doing, you have a parent and you are doing 3 forks. So what happens when the parent does the first fork? So parent will go on its own and a child will be created. Let's name it as C1. Now the second fork. So this part of the code will now be executed both by parent P1 and C1, right? So there will be another fork. So P1 will go on its own at P1 and it will create another child C2. Similarly, C1 will go on its own and will also create another child C3. Yes, whoever it is. Hi.
Sir, why we have 3P1?
How I have?
3P1, like
No, no,
P1
it is
first
not.
and then P1 and then P1.
So no, no, no. So the thing is, I am writing 3P1 means it is one entity. So what happens when you are doing a fork? So let's concentrate on this part. So what happened when you are doing the first fork? This is your P1, the parent. What happens when you're doing the first fork? It will create a child, right? And
Yes?
it will also have its own instance that is running, right?
Oh, okay.
Okay. So I am saying, so when you are doing a
But isn't it representing the second fork?
no, 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 no. That I'm so many representatives at different point of time. So what I want to do is I want to let you grasp it, that how the process fork occurs. So when you are doing one fork, so that means our duplication of the uh, program happens, right? So there was previously only one instance, now two instances are running. So one instance is your parent, another instance is your child. That's what I am trying to say.
Okay.
So
And how we will represent the second fork?
yeah, coming. So now, so
Okay.
so now, now there are two instances, right? One is the parent, P1, another is C1. So both will execute these two part, right? Right?
Okay.
Yeah. So now what will happen? Again, when we execute this fork, again there will be same thing, that it will be divided into two parts, right? One, the parent will go on its own, and another child will be created, right? For due to this fork,
Mm-hmm.
and same for this. So C1 will go on its own and it will create another duplicate of its own. Let's say C3.
Because we have C2, right?
Yeah. No, no, C2 will come. C2 will come. So at this point of time, how many instances of the program we have after these two fork? 4, the original parent, the first child, and the two new childs.
So we can say that C3 is the grandchild of P1,
Yeah,
right?
yeah, and same is C2. No, not grandchild. Yeah, you can say grandchild. That's no harm in that.
But not C2. C2 is the P1's
Yeah,
direct child,
yeah, direct child,
first child.
first child, correct. So that's why I'm making you understand like this. So so the next one, what it will be? This fork. Again, there will be a duplication, right? P1 will go on its own, and it will create another child. So what it will be? C4. C2 will also execute this. It will also have C2 on its own.
C5,
C5. Then again C1, there will be
C1,
C1 will be as C1, and there will be another called C6.
C6,
And C3 will be on its
C3,
own, and then C7.
and C7.
Yeah. So how many processes are created total? So total
7.
seven children are constructed due to it. So so you can write it like this: 2 to the power of 3 minus 1. So that's number of forks minus 1. Those number of childs will be created. But always I will say not to.
Okay, if we have 7 folks, then we will write to the power 7 minus 1, right?
Yeah, but here comes the catch. Think it about like this. Okay, let's keep this diagram and write a new diagram. Think it about like this. Fork, this is P1. If fork, 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 else fork. So what does this mean? So this part of the code will be executed only when only by the parent, and this part of the code will be executed only by the first child. Am I correct?
Yes.
Yes. So basically what I am saying is, this is P1. P1 will continue on its own, and then C1, and C1 will execute this part. P1 will execute this part, C1 will execute this part. So let's deal with how C1 works. So C1 will execute this fork. That means C1 will continue on its own, and it will create a child, another child, that is C2. Whereas P1 will now execute these two forks. What it will do? First fork, it will create P1 and another of its child C3, and this fork will again do the same. P1, C4,
C4, C3,
C3,
C5.
C5. So how many processes are created now? 5 processes, 5 child processes. C1, C2, C3, C4, 5, 5. So directly applying the formula is not a good way to visualize this. I will suggest that draw a tree and do it every time. That is better way of doing it. So now there are, so C1, C2, C3, 5. So there are 5 processes. Isn't the code similar to like this? Here also there are 3 forks. Here also we are doing.
Not really.
Not
Like
really.
we have
That,
four,
that,
more child in the second presentation.
yeah, that's what I am saying. That it is much better to visualize it rather than writing down the answer. So that is quite common that you will get such type of questions in GATE or not. That okay, so these 3 forks are given till the number of childs. So you will think, okay, so I remember the formula to the power of n minus 1 that way, but it is not always like that. You need to just visualize it and then do it. That way you will always get the correct answer.
How?
How means? So if you have
Like,
directly applied the formula here, will you have got the correct answer?
okay, but I have one question. Like, what if we have only one P1, and then we want to apply the formula? It's b to p1 to the power 1
Yeah.
minus 1. That is 1 minus 1 equals to
Yeah.
0.
So now why you are applying the formula? Because you have understood and visualized it. So formula will work for this part. Formula will work for this part, and formula will work for this part, but not at this all of them together. So it is always better to visualize it like this. Okay.
Okay.
Okay. So that's how your fork happens. Next, let's come to your another important way uh, to represent your, yeah, who, yeah, Said.
So where fork is executed?
Where fork is executed, what do you mean?
Like in microprocessors or registers or ALU
No,
or
this is
something
programming.
like
This is pure programming. This is done by OS. This is not architecture wise done. This is done by OS.
okay.
This is a programming construct. So process is basically a programming
So
execution.
compiler, so this process is executing in compiler, right?
OS compiler is the one that compiles it, but every program is run by the OS.
Okay.
Okay, so there is another. So other than fork, there is another system call, that is EXEC. One minute, let me find out this. Yeah. So so there is another system called EXEC. What EXEC does is quite similar to what fork does, but in a way different. So you want to execute, so you have written a program P1 and you have used EXEC P or something, and let's say you have said to list the list minus L. So list the number of files. To list the number of files you have said. So what happened in this case? This process has a process ID. Process P1 has a process ID. So when it executes this EXEC, so what happens in that case? So this creates a process, and it will have its own PID. Let's say PID2 and this is PID1. So what this process P1 does, it takes hold of this process and eliminates what it has have. So whatever it has written in it, it dumps it, and P1 now takes uh, the hold of this thing, this process PID2, that is EXE ls minus L. This is another way of creating a process. So whatever image it had previously P1, it dumps it and takes whatever you have written inside the EXEC ls minus L. So this is another way of creating a process. So any doubt regarding this? Fork and EXEC? Yeah, Said.
So why we need to create process?
Any program you run is a process. The definition of process is a program in execution. So you are viewing this in your Google Chrome. Google Chrome, you go and check behind. It is a process. Process is basically a program in execution. So whatever program you have written, it will execute and run as a process. So whenever you are
And process and thread is related to process.
uh-huh. Hello.
Is thread is related to process?
No, thread is different. We will come to thread. We will come to thread.
Oh,
So thread is basically a lightweight process. So if you have gone through the previous lectures, which
okay.
so you will see that a process can have multiple threads. So okay, let's discuss the thread also. So a process has its stack, heap, and data, and different process, another process. So suppose you have written a program prg1, and this is its one process, this is another process. So each process will have its own stack, heap, data. Now this process can have multiple threads. So so uh, so the the major definition or the difference between a process and a thread is that multiple threads, thread T1, T2, T3, will share the same memory space with that of the process. So T1, T2, and T3 will share the same memory space, whereas P1 and P2 will won't. They don't share the same memory space. They have different memory space for their own work. So that is the major difference between a thread and a process.
So this is look like main memory architecture.
Yeah,
Like
yeah. So at the
like we have data of code, then stack, and then extra.
yeah,
Right.
yeah, it is quite similar. So at the end of the day, OS has to interact with the hardware for operating every programs and all. So when you will come to the end of the lecture, like in week 10 or 12, you will come across the same concepts of cache and virtual memory, which you will get in the computer organization and architecture course. So those things are related, and it is very much preferred that those are taught in the same breath as this OS. Okay. Okay, so let's come to the next part. So that is inter-process communication. So a there may be scenarios where multiple processes has to communicate with one another. So suppose you have your Google Chrome, and uh, your Google Chrome, what it does that it opens multiple tabs, and each tabs are a single process of its own. But the but what happens is that Chrome needs to communicate with one another, the different process. Suppose you are on one website, like say uh, uh, a song library website, and you want to download a file, and let's say you are on an online library of books, and you want to download an ebook. This download feature is common to both of them, okay, but suppose they need to keep it in some memory space, and that memory space is very limited. So this processes needs to communicate with one another, so that it does not one does not affect the operation of another. So that is why inter-process communication occurs between the processes. So how does a process communicate? There are two common modes of process communication. One is shared memory, another is message passing. So what happens in shared memory, the process A and process B share a single piece of memory, and whenever it has to like communicate with one another, it writes that thing in the shared memory space. So that suppose process 1 A wants to tell something to process B. So what it does, it writes down in this shared memory what it wants from process B. Process B checks that memory and and gets to know, oh, process wants something from me. Okay, let me write it down to process what he wanted from me to this shared memory again. Then process A checks again and sees, oh, process B have written it down. Okay, that this is what he wants to communicate. So this is how the communication occurs between process A and process B through the shared memory. Now, also there is message passing. So what happens in message passing is that a channel is opened uh, in both ends, so that so it is kind of a queue. Let me explain it. So in a shared memory, you have this memory space, and you have your process 1 and your process 2. Now it wants to communicate something, some data from P1 and P2 and P2 to P4. So what it does, P1 writes what it wants to communicate here. What P2 is does, P2 reads this part of the memory and sees what P1 wants to say. That's how it gets its data. Now P2 further wants to communicate something. P2 further wants to communicate something to P1. What it does, it writes in that shared memory. And then P1 takes that from the shared memory. So this is how in shared memory concept occurs. Now in message passing, so what happens in message passing is that you have a queue. This is process P1 and this is process P2. So what happens, this is a bidirectional queue. So the flow can happen this side to this side, at the same time can happen this side to this side. So what happens in the this bidirectional queue, P1, if it wants to send something to P2, it writes that in the queue. And P2, if it wants to receive something from it reads from the queue, and same the vice versa. So if you remember your queue, what is a queue? It is a first in, first out. So always the one that is on the top will always be taken, like the first element that has been passed in the queue by P1, P2 will be will take that first element only, not the some other element. So this is the difference between shared memory and message passing. So any doubt regarding this shared memory and message passing? Okay, so let's look at the shared memory. Shared memory has a area of memory among the process that we used to communicate. The communication is done under the control of user processes, not the operating system. Then there is synchron. So communication is basically synchronization of the data items that is done through this buffer. So this is a bounded buffer concept. So uh, So this is a buffer. So this is how a buffer looks in your for the case of data sharing, shared data. So this is a buffer, and then there is a list of items. So this is your array of buffer. There is the number of ins and out channel. So this is how the buffer is filled. So uh, in minus plus 1 is buffer size is not equal to out. So the next produce is say put in the buffer. This is the how the buffer is filled, and this is how the item is taken out from the buffer. So from buffer out to the next consume, and the number of count is incremented. So this is called the producer consumer concept. So the producer produces the data that is stored in your buffer, and the consumer consumes the data that is stored in the buffer. So so in this case, here is the buffer kept, and here from here the buffer is taken, and same is here, and here is also same. Here the buffer is put, and here P2 takes it from the buffer. So message passing is similar to, so you will have two operations, send and receive. Message size is either fixed or variable. So if process P and Q wants to communicate, they establish a communication link between them, exchange message via send or receive. So implementation issues are there, like how the links are established, how many links can be associated with the process, what is the capacity of the link. So if the link unidirectional or bidirectional, these are some of the issues related with it. So it can be physical, like hardware bus or thing, or logical, indirect, like that. The process must name each other explicitly. So the send P message is sends a message to process B. So this naming is basically done through process IDs, and same receive a message from process Q, like this, these commands. So we'll see some problems related to this. Message are directed and received from the mailbox. Primitives are a message, send a message to mailbox, receive a message from the mailbox, indirect communication. Then there is blocking and non-blocking. Blocking send is the user is blocked until the message is received. Non-blocking is the sender sends a message and continues. So typically a blocking or non-blocking scenario is like this. So uh, in a blocking is the sender sends a message, and the receiver accepts it as if it is waiting for it to accept. So that is a blocking message. So the receiver will wait until and unless it receives a message from the sender. That is a blocking send and a blocking receive. Whereas in non-blocking, it is a asynchronous way. So you can send a message anytime, and as you can receive the message anytime. In the between time, the process can do some other works. Okay, so this is what blocking and non-blocking schemes are. Okay, so let's look at some code for message queues. And so this is a message queue. So this is you can see this is the structure of the message queue. So this is your type of message, and the message text. This is your one of the code for message queue. So so here is your message send function in Unix, how to send a message. So you need to give the queue ID, the queue that you have created here IPC creating the IPC message queue, and you send the message and message sent. Then you receive a message and message received. This is you how you send and receive a message. So note that this is a blocking message send and blocking message queue. You are sending a message when you want, and you are receiving a message whenever when you want. So you wait at this point until and unless the message is received. You wait at this point unless the message is received. This is a non-blocking way of receiving a message. So this is the server in a message queue, and now here is the client. So what is the client do? It receives a message and it then sends a message. Just the opposite. So it is like this. So you have the server process and the client process. So it sends a message and receives a message. So in the current example, it is a blocking process. It sends a message and it is wait until it receives a message to that person. And the same vice versa happens in the other direction. Message sent, message receive. Now there is another concept. So as I described, message passing is done via a queue. So you need to write the message in a queue, and then so server write the message at the queue and the client receives it from the queue, and it follows a FIFO structure. Now you want to send a priority message. So whatever currently that is being sent, that is okay, but you want to send something that is very important for the client to receive. So what you do in that case? You set a priority for that message. So instead of using a regular queue, you use a priority queue to implement it. So you send a message and add some priority to it, and the receiver in that case receives that message first before any other non-trivial messages. Clear? That is how message passing works in Linux between the processes. So any doubt regarding this? Okay, so let's go to the next thing, that is the shared variable, shared memory. So this is the memory. So as you know, the processor has its own memory space. So suppose one process is sharing the memory from this address to this address, x3000 to 5000 and 50,000 to 7,000. Among it, it shares a piece of memory that is common to both of them for both process A and process B. So this is the place which is used for communication between them. So, so using CHM gate, one gets the memory. Using CH map, it attaches it to the memory, and using CHM detach DT, it detaches it from the memory. So here is your a code which is used for this memory sharing purpose. So using this CHM gate, it makes the memory segment. Using CHMAT, it attaches the segment, and then it using CHMCTL, it removes the statement. This is how uh, shared memory works. So basically, what this slide say is that this is process P1. It has a memory space, and process P2 also has a memory space. Now, a small part of this memory, let's say this section, is shared between P1 and P2. So by utilizing this shared portion of memory, the process P1 and P2 communicates. So this is the concept of shared memory. Now you uses those statements like CHM get to get this memory, then CHM attach to attach to the memory, and then CHM detach. So why you need CHM attach and detach? What does this does? So since this is a shared portion of the memory space between P1 and P2, only one can like access it one at a time. So only one person can access it one at a time. So that both cannot concurrently access it and does something evil with that code, CHM attach and detach is used so that only one process can access it one at a time. That keeps the sanity of this system. Okay, so any doubt regarding this IPC things? Both both of them shared memory and uh, your message queues.
So can you back to the share memory slide?
The code or the slides?
Slides.
Yeah. This one.
No, it's not that.
Here, okay, let me go through it again. Bounded buffer. Yeah.
No, not this one. The slide. We have that graph kind of picture of shared memories like
Oh, okay, okay, okay.
P1 and
I
P2.
understood, understood. This one.
Yeah, this one, this one. Okay, great. And these both are main memory,
Hmm. Main
process
memory.
A and process B.
Yeah, main memory.
And what is this shared memory and region where it is located?
main memory. So these are address location, address space. So these access these so
This is a code segment, right?
huh?
Is this the code segment?
No, this is a memory map. So the process A have this memory space that it can access, and this process B has this memory space that can access. So out of which this is the shared part of the memory. So the thing is,
Okay.
so
So
so you need to understand this.
process A can access process B and process B can access process A, and that part,
Yeah,
like
only
the
that part. So
our
so
but
so so let me yes. So you have your main memory. This is a very large chunk of memory, right? So currently your system like this, my laptop has 16 GB memory, right? This is a very big space. So one of your process needs 400 MB of RAM, and process P2 has also needs 400 MB of RAM. So it will take some chunk of this memory P1. Sorry, let me use another. So it will use this chunk of memory, let's say for P1, and let's say it uses this chunk of memory for P2.
sir, do you have any picture from Google so I can understand better?
Uh, Not Google. I can have only this picture. So shall I draw it better?
Yeah, right.
Uh, okay, let me let me draw it better. Okay. So here is your process P1, and here is your process P2. Now here is you have the main memory, right? So we all know process has its own memory, right? So P1 will have its own memory, and P2 will have its own memory. Where does this memory comes from? This comes from your main memory, right? So there are lots of memory space inside this. So it is basically, let consider it as a table. So it has lots of memory space inside this. It is actually in from a table. I'm just saying like this. So what OS does? What OS does is it allocates one such block of memory to P1. Yeah, hi. Yeah. So what what it also does is it allocates another chunk of memory, let's say this one, to P2, right? So this is how your process gets a memory. It comes from that same chunk of main memory. Only some different portions of the memory are given to P1 or P2. Now here comes the what we are saying is that P1 and P2 needs to communicate with one another. How to do it? So what 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 it does at that time, one such process is shared memory. So let's consider this portion of the memory is shared by both P1 and P2. Let's assume this chunk of memory space is shared by both P1 and P2. So the problem is the same memory space are used by P1 and P2. So it needs to maintain some kind of sanity so that both are not accessing the same pace of memory at the same time. If that happens, that means there will be corruption, right? Data corruption. So if these P1 and P2 try to access these at the same time, this will lead to corruption. So one easy way to do this is via is via shared memory. So shared memory gives like this attach slash detach statements such that, so suppose if P1 issues attach, only at that time point of time only P1 can access this part, and unless and until it issues detach. Once detach is done, P1 says, okay, my task is complete, I don't have to share anything anymore. Now if P2 gives an attach, then at that time it gets hold of it and P1 cannot access it until and unless a detach occurs. So this is how the shared memory concept works. Now you understood, Saeed?
Yes, sir, a little bit.
A little bit. You say, ask what you don't understand, you ask, I will say.
Uh, I need some time to understand this. Like
Yeah,
I will study more of it.
what you can do is you go back, this session is being recorded, okay? So you go back and again rewatch this, and you can also,
Yeah.
yeah, you can also go through the slides. I will attach the slides for with the code, okay? So those codes are very important to understand how it works. So you go through
Okay.
it and have uh, also you can watch this week's session to understand how message passing and this works.
Okay.
Message passing you understood, right? We uses queues to do it. So you are just inserting into the queue. One process is inserting into the queue, another process is taking out from the queue. Again, the same thing happens. One process is inserting from the other end, and one process is taking out from the other end. Okay, so let's come back to our slides. So IPC we have done. So now let's come back to pipes. So the problem or the flexibility, so let's say the flexibility with what you got with message queue is that it's a bidirectional way. So 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 it is using doubly linked list so that you can,
Sir, please maximize this slide.
yeah, okay, sure. Now fine.
Not zoom it. Just maximize it from right side.
Maximize in the sense.
From right side. Just
So this is the maximum, right? This way you can see the full screen.
not, just look at the setting icon, and before that there is a sign to
No, you are.
maximize it.
It is still not visible.
Not clearly, like I can't see clearly with some distance.
Well, this is the maximum slide. Okay, so this is the maximum size. After this, it's not
Okay.
possible. Okay, so the pipes. So the thing about pipes is, uh, so let's go back to the diagram. Message passing done. So In message passing, what we are doing is we are using a bi-directional queue using doubly linked list. So you have your linked list here, you have your linked lists here, and it is bi-directional. Okay, so P1 and P2 can communicate in both ways. So P1 can P2 can send the data, and P2 to P1 can also send the data. Now the problem, this is a very like better way of communication between the processes. The other way is your pipe. The problem with pipe is it is just a unidirectional flow of data. So it can at a time just flow data in one direction. So P1 to P2 it will be just one direction. P2 to P1 it cannot send. To send in the other direction, this is pipe 1, it has to install another pipe to do it. Pipe 2 to send flow data in this direction. So whereas in one message queue you are able to send data in both direction, in pipe it is not possible. It sends data only one direction at a time. So that is how pipe works. So pipe acts as conduit allowing to process to communicate. Issues is communication unidirectional. So pipes you can see consider it as a writing to the file. So producer writes to one end and consumer reads from the other end. Pipes are unidirectional. Only one way of communication is possible. If two-way communication is required, two pipes must be used, not one pipe. Requires a parent-child relationship between communicating. Where message passing and shared memory does not need it, the pipes requires parent-child relationship to communicate between one another. This is how pipe works. So this is your two file descriptors you have to use, FD0 and FD1, and the parents has FD0 to read to the file and FD1 in the other one. So data flows only in one direction at a time. Now, communication in client server systems. So, you want to communicate between two processes, but they are in different systems. So, this is my system, and I want to communicate with, let's say, your process. So, pipes are clear, right? Then we can go to sockets. If you have any doubt regarding pipes, you can ask. Okay, so let's go to sockets. So sockets are basically used for network transmission. So suppose this is my laptop. I want to communicate to a process in another laptop. So in that case, sockets are used. So sockets are associated with your IP address for this purpose. Sockets are inter-process communications, but between processes in different systems, not in your same system. So a socket has a endpoint for communication. So it has socket is basically, so the ID in that case is a concatenation of an IP address and port So this is your IP address and concurrented with your port, that is 162.5. There are some special IP address and all for these purposes. So this is the communication. So this is your host computer machine, and here is your socket ID, and this is your another web server. This is a different socket ID, and this is how the process communicates between one another. Other than that, there is this remote procedural call that calls between processes on network system. Again, it uses ports for communication. Client-side proxy is required. This is quite similar to socket programming, but it's a abstract procedure call between the processes. It's not directly using a IP address and password to do this. IP address and let's say socket and like ports to do this. So here is your here is the execution flow of an RPC. So user calls kernel to send RPC to message to procedure X. Kernel sends the message to the matchmaker to find the port number. So this is the message that is sent to the server from client to server. Port this address for RPCX. So it looks up an answer. Our matchmaker replies to client with port P from server to client regarding RPCX port P. The kernel observes the port P in the user RPC message. Kernel sends message. Now it directly sends the message to the port. So previously it was working with the matchmaker, then with the client with the kernel. Finally, it directly happens between the port address given by the server to send the data. So a very easy way to say is that the client first doesn't know what is the port address, so it asks the matchmaker which is there in the server, okay, give me the port. The server sends it the port, say this is the port where you can send the data. Then RPC sends the data directly to the port, and then the kernel receives that okay, all data has been sent successfully. This is the flow of RPC. And finally, this is how your process is memory layout of your process. So at the top of them you have your global variables like argc and argv. This is where, so this is the malloc portion that is present in your heap. These things are in your stack, and this data, these global variables are present outside. So this is the typically the memory layout of your process. Okay, so that's your all about processes and process communication. Now we will come to threads. So any doubt more regarding the processes, then we will come to threads directly.
No, sir, come to thread.
Yeah, so let's look at threads. So this is your single threaded process and this is your multi-threaded process. Notice the term process. So basically process is the same for all of them. So be it one thread, two thread, four threads, anything, there will be one process. So you can consider parent as the superset of all the threads. So in a single thread, so what is there in a process? A process has a code, a data, and the files, but it has its own registers and stack as well. So here is a single threaded process. Now when it becomes a multi-threaded process, so the code, data, and the files are same, remains the same. It is not duplicated, but the thread has its own registers and stack. So this is the main difference in the architecture of a process and a thread. So while the mm, so while a process can have only one thread, when it has multiple threads, the code data files remain same, but the threads will have their own set of registers and stacks. Understood this part?
Yes, sir.
This is quite clear. Code data files are the same. Code data files will remain same. Each thread will have their own register and stack. Let's assume a multi-threaded like let's assume you are using Facebook. Okay, so you have joined to Facebook. You are asking Facebook, okay, open me this profile. What Facebook will do to serve you that profile, it will give it will in its server it will create a thread to for your request. So while the code and the data and everything remains same, you will get your own registers and stack to execute it. At the same time, server will keep request listening to additional requests from other clients. So in this case, the client is you, the server is the Facebook, and it's a thread of that server. This is how multi-threaded server architecture works. So what are the benefits in responsiveness? So so if you are creating multiple process, what it happens? So if you are creating multiple process of the same program, what will happen? So basically it will require more memory space, because this data will be duplicated, the files will be duplicated. So this 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 architecture will just keep on growing if you are using multiple processes. So assume you are using a browser, and for each tab it is opening a process. So at the end of the day, your memory space increases as and when you are increasing the number of tabs. But instead of when you are opening a tab, instead of creating a process, if it creates a thread, those are much lightweight compared to a process. So the code, data, and the files remain the same. The registers and stacks are only duplicated. So it is much cheaper way to do it. So that is one of the main memory benefit. And then there is resource sharing between the processes. Thread share process resource of the process, that is the same thing. Economy, that is cheaper than process creation. Thread switching, or these are low overhead things. And scalability, process can take advantage of multi-process architecture. Then there is
So
multi-core. Yeah. Say.
can we discuss thread more deeply? Like in architecture, we have threads with cores.
Yeah. So I know that next in week 5 it is completely on threads, POSIX threads and all. So we'll come back next week to that threads.
Oh, okay.
So I have seen the syllabus. So next week there is threads. So this is just an introduction on threads, nothing more. Okay. So multi-core and multi-CPU programming, we have talked about it. So one CPU have multiple cores, and whereas a single computer have multiple CPUs. So think about it as your phone. So whenever you buy a new phone, you will see a feature that comes up: multi-core, octa-core processor, Snapdragon processor, octa-core Snapdragon processor. What does this octa-core Snapdragon processor mean? So that means the CPU uh, that Snapdragon has produced, it has 8 cores. So those 8 cores are basically its programming units. So those single processor chip can have multiple cores. So a program can be run in one of the 8 cores as and when required, and the CPU schedules it accordingly. Now, what is a multiple CPU system? The thing is, like in big servers there are more than one CPU, not one CPU is there. So so a CPU, let me give an example, like like a big Windows server can have two different kinds of CPU at the same time. And to mm, like these servers for your, let's say, Flipkart or Amazon, these are multi CPU systems, these are not multi core systems, because they need to keep multiple CPUs to organize and uh, run more than one program at a time. So those are much more heavy. So these are the features of your multi-core programming: data parallelism, task parallelism. So a multiple threads can be run on multiple cores at the same time, so as to speed the things up. So these are the different features and nothing more. Dividing activities, balance, data splitting, parallelism, concurrency. Those are the things. Okay. Okay. So let's come to the problem solving part. Let's solve some MCQs. So the question one is, a process can be terminated due to a normal exit, fatal error, created by another process, all of them. So what is a process? Process is basically a running program. So what is a normal exit? So basically you have written a program and it runs all the system, all the statements, and it ends. So that is a normal exit. So that's a way process can be terminated. Fatal error. So suppose you are running the code and suddenly a error occurs, like let's say divide by 0. So that is a, or let's say you are some thing happens, like out of memory error comes. So when this kind of error happens, the process is killed. So these are fatal errors. The process can be terminated by a fatal error. Killed by another process. What do you mean by killed by another process? So what, there is a specific command uh, in your bash. Bash provides you the specific command called kill. So in kill you need to give your process ID to kill a existing process. So basically this bash program basically uses this kill command to terminate a process. So process can be terminated by another process. So the correct answer is all of the above. Okay, so let's come to the next question. A process stack does not contain what? Function parameters, local variables, return address, PID of the child process. So the question is, what does a process stack does not contains? So your process has stack Keep files code global variables. So what is the stack used for? So stack is used for context saving, to understand which is the next part of the code that will be executed. So if you are doing a function call, what are the up to which point the code has been executed, that part gets stored here, so that after the function call it can return back to this original program. So if you have written a code int x equal to 100, and you have written a factorial program, factorial of x, so it needs to save the context up to here, so that after this factorial get executed it can come back and join here. So so this is what the things that are stored on stack. So the things that are stored are basically, yes, functional parameters are stored. What are the parameters that are passed to this function? Local variables, this x is stored. Return address, so where it will return after completing this, where it will return? It will return here. This part of the code has to be executed, so it knows the return address, but it does not know the PID of child process because that is not required. So the process stack does not contain PID of the child address, PID of the child process. Yeah. So uh, the program fragments prints string prints hello how many number of times? Yeah, good question. So how many times this port of the code produces hello? Give me some answers regarding this. So what happens? So this is your parent. So your parent comes here and it does a fork. So fork is equals to 0. So that means this if, what is inside this if statement will be only be executed by your child. So this parents create a child by this fork. So this is p will continue and this is your child 1. Now what happens here? So after this fork happens, this child performs another fork. So that is C1 will remain C1 and C2 will be created. So how many times this hello will be printed? It will be printed by P, it will be printed by C1, it will be printed by C2. So the correct answer is 3. This one is clear? This is very important because any competitive.
Not really, sir.
So what happens when this part of the code? So you need to tell me when this part of the code is executed. When fork.
But we are executing just single process, right?
Yeah. So
Then why a child one is creating their own child?
yeah. So you have, this is your program. Let's say P. Okay. So this is your P. Here comes your if statement. So in that the if statement, what you are doing? A fork. You are doing a fork. What does a fork produces? Fork produces a child. Let's name it C1.
Hmm?
And it remains as it is, right? The P remains as it is, right?
Hmm?
So when does the fork give zero? Whom does the fork give zero? The fork gives zero for the child. So that means this part of the code will only be executed by the child. So
Hmm?
so here comes another fork. So that means C1 will remains as it is, but
And then
it creates another process C2. Now it exists, these all three programs exists, this part, and it comes to here. Here, which was this program? Pu is there, C1 is there, C2 is there. So how many times this will be printed? Three times. P, C1 and C2.
but if fork is not zero and this is going to
Yeah,
one.
so okay, so let's discuss that one also. Okay, so let's consider the, let's consider the portion for not equals to 0. Fork, if fork not equals to 0, fork print hello. So in what will happen? If fork equals to 0, so p is remains as it is. So it creates a child p c1. Right. Now this part of the code is executed by the parent. So it does another fork p
Hmm?
c2. Right. So then it comes here. So here also the same case happens. P c1 and c2, three programs. Just you see the structure is different. Here C2 is the child of C1 P, and C1 is also the child of P, but here C1 C2 is only the child of C. This is the difference. So in this case C1 and C2 are both child of P. Here C1 is the child of P,
Of
C2 is the child of
child of C1.
C2, C1, sorry. C1 is the child of, C2 is the child of C1. So that is the rest difference. Now it is clear, the graph structure and all.
Hello, sir.
Yeah,
Hello.
yeah, you can say.
Sir, can you hear me?
Yeah, I can hear you.
Sir, what is fog? Actually, sir, this is my first class, so what is fog?
Yeah, so fork is used for creating the processes. Okay, so I will recommend you to like, have you gone through the lectures? Like it is more important to go through the lectures once. So so
Okay,
so
sir.
so,
Thank you, sir.
in simple terms, fork is basically used to create a child process. So process is basically your program in execution. So when you use a fork, it creates a,
Yes, I know processes.
yeah, so another child process is created. So it will have its own address space and everything, which is just a duplicate of your process. Only thing it will be different will have is a process ID. That is the only part that will be different from that of the process. Fork is used just to create a child process. Yeah.
Sir, in if fork is not equals to 0,
Hmm.
in that case, why C1 is not creating C3?
Uh, Fork is not equals to 0. Which statement you say?
Like we have if fork not equals to 0,
Yeah.
okay, we have 2p, we are creating in that two, the last one, the last case.
Yeah.
Okay, then why C1 is not creating another their child like C3?
No, 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 no.
Yes,
So you need to understand how this fork happens. Okay. So so fork, you need to understand how fork works. Else this will be very difficult. So consider this statement, and let's say, so I will recommend you to go and run the codes. Okay, so that will help you more. Switch case 0 and default. So what does fork return? Fork returns 0 to child process, and PID of child process to parent. So here, after this code will be duplicated in two parts. Same thing, switch PID case 0 default. Let's say this is your parent and this is your child. So what will be the PID in case of child? It will be 0. Fork return 0 to the child process. So in case of child, this case 0 will be executed. So here will be hello child, and that in the, suppose say here it is hello parent. So in other case, there will be a number associated, identifying number associated is passed to the switch statement, and it in that case it will print the hello parent. So now you understood, right, how fork duplicates the thing, the uh, process, and how it creates a child.
yes,
Okay. So so here it's 3. So let's come to another example. So how many times hello will be printed in this case? Think about it. And so here is your, let's say, parent. So here is your parent. It does the first fork. It does this fork. It creates one copy parent, another copy child. Now both will execute. So both has this copy of this. This is has P and this is C. It has fork and then it has printf statement. So P does this fork and it creates another child C2. Now P has P has printf, and as well as C2 has printf. Now let's come to C1. C1 also has fork. It now has, it keeps C1 as well as it creates another C3. So what C1 and C3 will have now? This statement C1 printf and C3 printf. So how many times this printf will be called? P, C1, C2, C3. So four uh, hello statement will be printed. This one is easier, right?
Yes.
Okay. So let's go to the next problem. So in Unix, for system call returns. Okay. Now we discussed. It returns a value 0 to the child process. True. It returns the process of the child process to parent. True. It returns a value of 1 to parent process if no child process is created. True. So the correct answer is all of the above. Okay. So which of the following is not correct about thread of any process? Compared to a process, switching between threads of same process takes less time as the quantum analysis. So yes, true. Because threads are lightweight. Threads are lightweight. Inter-thread communication is faster. The threads of one process uh, is shared address space. Uh, so inter-thread process communication is faster as the thread of one process is shares the same address space. Yeah. So as we have seen in this slide, let me bring the slide back. As you see, these the data and the code, these data are shared between all the threads, the same data. So as a result, the communication is much faster in case of multiple threads. So this one is also correct. Threads of a process share the same address space. Threads of a process share the same address space. True, the data address space is shared, so this is correct. Compared to process, switching between threads of the same process takes less time as compared to as next to run threads share the same address space. No, switching of threads of same process takes less time. No, the takes less time because of its lightweight nature, not because it is shared between the sharing the same address space. So A, B, C are the correct options. Next is pipes provides a way of communication among processes. Which of the following statements do not hold true about pipe? In pipes, communication can be bidirectional. It can be, but in most cases, it's unidirectional, but it can be bidirectional. So to make a pipes bidirectional, you need to use two pipes. So one flows in this direction, another flows in this direction. So no parent-child relationships are required in ordinary pipes. No, it is wrong. So the thing is, in pipes, you need to have this parent-child relationship, else it will not occur. While in message queue and uh, shared memory space, they don't need to have this child parent concept. This needs requires. Ordinary pipes provides a simple communication of mechanism between a pair of processes. Once a named pipe is established, several processes can use it. So ordinary pipes is a simple communication mechanism between a pair of processes. Once a name is established, several processes can use it for communication. True. So so basically it is a parent-child relationship. So so if there are more than one child to the parents, it can communicate with the same pipe. It doesn't have to use different pipes. In that case, a proper mechanism is required to coordinate this thing. IP interprocess communication mechanism techniques are uh, intercommunication places that are pipes, signals, and message passing. So these are the three. So we have seen pipes and message passing. Signals will be covered in the next few lectures. So how concurrency differs from parallelism? So concurrent systems allows more than one task to run while parallel system doesn't. No. Concurrent system means you have a simple uh, you have a you have a task and it requires the same area to run. So multiple tasks can work at the same time. So that is how concurrent works. In parallel, it's different. Parallel, each can have their own unit to run. So that is parallel. So the correct answer is this. Concurrent system can allow more than one task to run, whereas parallel system can perform more than one task simultaneously. So which of the following is incorrect about named pipes? So pipes is a concept which only one process can use a named pipe from communication. So bidirectional is allowed, provided on both on Windows and Unix. No parent-child communication is necessary. It's no, it is required. Only one process can use the named pipe from communication. No, more than one can use. So as one process can have multiple communication through to the child through this. User threads are supported. Uh, so so user threads are threads that are created by users, and then there are kernel threads which are created by kernels. So user threads are above kernel and are managed without kernel support. So users can manage it. So this is the correct answer. So they do not require kernel support. They can be done managed by directly by the users. So remote procedure calls are used for communication between processes, two processes remotely different from each other on the same system. No. So remote procedural calls are done for communication on separate systems. This is the correct answer. Okay. So with that, we come to the end of today's one. So we'll again meet next week. Thank you for joining.